In this video, we're going to discuss valence bond theory. So valence bond theory is defined as a quantum mechanical model which shows how electron pairs are shared in a covalent bond. So essentially what it's trying to do is explain what happens when two atoms form a covalent bond. According to valence bond theory, a covalent bond is formed by the overlap of atomic orbitals from two different atoms. Each orbital must contain a single unpaired electron, and the two orbitals must have electrons with opposite spins. The overlapping atomic orbitals must be in the same phase, and the bonded atoms, the two atoms that are forming the covalent bond, maintain their own atomic orbitals, but the electron pair is shared by both atoms. Furthermore, the greater the amount of overlap between the two atoms, the stronger the covalent bond. So let's take a look at a couple of illustrations. Let's take a look at two hydrogen atoms. Here we have a 1s atomic orbital for each hydrogen atom, and each hydrogen atom contains an unpaired electron. You can see they have opposite spins. When these two hydrogen atoms form a covalent bond, we of course form an H2 molecule. The covalent bond is formed when the atomic orbitals overlap. You can see them overlapping here, and they share the pair of electrons. You can see the electrons have opposite spins, and they're located in the region of overlap, creating our covalent bond. Let's take a look at another example. Here we have two fluorine atoms. We're not showing all of the atomic orbitals, we're only showing the 2p atomic orbitals that have the unpaired electron for fluorine. So here we have our two atomic orbitals. Each of our atomic orbitals has an unpaired electron with opposite spins, and you can see that the atomic orbitals are in the same phase, indicated by the same red color. When these two atomic orbitals overlap, we form a covalent bond and therefore form a fluorine F2 molecule. The covalent bond again is formed by the overlap of the two atomic orbitals, and the pair of electron is shared in the region of overlap. You can see again the electrons have opposite spins, and they're in the region where the two atomic orbitals overlap. So here we have another covalent bond. One thing you might notice is that with the overlap of the p orbitals, there's not quite as much overlap as there is when we have our s orbitals overlapping. So valence bond theory would predict that this bond is a little bit weaker than this bond because there's not quite as much overlap. One other thing, we call this a sigma bond. So these covalent bonds where the two atomic orbitals overlap directly parallel to one or directly head-on to one another, we call those sigma bonds. So what if we have a molecule that has more than one covalent bond, something like methane, which has 4 covalent bonds? How does valence bond theory explain the bonding pattern here? Well, one thing that a valence bond theory requires is that for our central carbon to form 4 covalent bonds, we must have 4 unpaired electrons. Well, if we analyze carbon's ground state electron configuration, we see that carbon doesn't have 4 unpaired electrons. The valence electron configuration for carbon is 2s2, 2p2. So carbon, according to valence bond theory, might not be able to form covalent bonds, or at least 4 covalent bonds. Well, one thing that could happen is that one of our 2s electrons becomes excited in the bonding process and jumps up into one of our 2p orbitals, creating an excited state electron configuration. Now we have 4 unpaired electrons, but note one thing, the electrons have different energies. These 2p electrons have higher energy than the 2s, so that's going to create a problem. Let's look at that. So undergoing the excited state electron configuration would allow carbon to form 4 bonds. but the bonds would not be all the same, since the electrons are not all in the same type of orbital. 3 of the bonds formed by our carbon would be formed by the overlap of its 2p orbital with hydrogen's 1s. So we could form 3 covalent bonds by overlapping carbon's 2p electrons with one of hydrogen's 1s. But the other 4th bond would be formed by carbon overlapping its 2s electron with one of hydrogen's 1s. So this bond, the bond that's formed by the overlap of the 2s and the 1s, would be different, have different strength and different bond length than the other 3. Well, we know from studies that methane has all 4 of its bonds are the same strength, the same distance, bond length, and so there must be a problem. This must not be the answer. So how can carbon form 4 covalent bonds, all with equal bond strength and equal bond length? Just exciting one electron up into one of our 2p orbitals would not explain that. So what valence bond theory says is that our atomic orbitals undergo hybridization, or they become hybridized. So in the bonding process, our atomic orbitals, these 4 atomic orbitals, all combine together and form 4 brand new atomic orbitals. And we call these hybridized orbitals. And these are formed, as we mentioned, by the 1 2s and the 3 2p orbitals, all combining to form our hybrid orbitals. So we form 4 hybrid orbitals, and since they're all the same, they have equal energy, they would be able to form 4 equal bonds. And we put, carbon has 1, 2, 3, 4 valence electrons, so we put our 4 electrons into each of our 4 hybrid orbitals. We call these hybrid orbitals sp3 hybrid orbitals, and we do that because they're formed from 1 s orbital and 3 of our p orbitals. So they're 1 part s, 3 part p hybrid orbitals. Now there are other types of hybrid orbitals, and we'll discuss those later, but for carbon, when it forms 4 bonds, it undergoes sp3 hybridization. So here's another look at that. Here's an s orbital, and here's our 3p orbitals. Remember that what their shape looks like. Those guys all combine, those atomic orbitals combine, and we started with 4 atomic orbitals, so we have to end with 4 atomic orbitals. And you can see that these hybrid orbitals, they look a little different. They look a little bit like a p orbital, but one of these lobes has kind of shrunk a little bit, and that's because it's taken on a little bit of the s character. And these 4 hybrid orbitals would form a tetrahedral geometry. So all 4 of these would be tetrahedral to another. So now we have our 4 hybrid orbitals represented here in blue. Each hybrid orbital has a unpaired electron. And now our hydrogens, which all have unpaired electrons, each of our hydrogens can form a covalent bond by overlapping with one of our sp3 hybrid orbitals. So we could visualize methane a little more accurately by looking at it like this. We have a tetrahedral geometry, and our covalent bonds are formed by the overlap of an sp3 hybrid orbital with one of hydrogen's 1s orbitals. And again, we call these covalent bonds sigma bonds because they're basically a direct head-on overlap. We'll see that there's other types of another type of bond, and we'll discuss that a little bit later. So let's take a look at a problem. Determine the hybridization for an ammonia molecule and draw a picture accurately showing all of the bonds and the correct geometry, kind of like we did for methane. Pause the video and give it your best try. See what you come up with. Okay, so for ammonia, the first thing I would always start with is to draw our electron dot structure. So we get an electron dot structure for ammonia that looks like this. The second thing I would always do is determine the number of electron domains around my central atom. For nitrogen, I have 1, 2, 3, and the lone pair counts as 4. So I have 4 electron domains, which gives me a steric number for the nitrogen of 4. So that's going to help me determine my molecular shape and the electron domain geometry. Now for hybridization, this is important. For this particular molecule, we have 4 electron domains. We require 1 hybrid orbital for each of the electron domains. So for here, for ammonia, since we have 4 electron domains, the nitrogen must form 4 hybrid orbitals, all with equal energy. So before we do that, let's look at the electron configuration for our central atom, for our nitrogen. And we see that nitrogen has a 2s2, a 2p3 electron configuration. So now, determine the hybridization for the nitrogen. Well, we mentioned before, just a minute ago, that nitrogen must form 4 hybrid orbitals. And so in order to form 4 hybrid orbitals, we need to use 4 of our atomic orbitals, 4 of our valence atomic orbitals. And so we're going to take our 2s, that'll be 1 atomic orbital. We're going to use all 3 of our 2p atomic orbitals. And so we're going to form 4 sp3 hybrid orbitals, just like we did with methane. So we took 1, 2, 3, 4 atomic orbitals, and that allowed us to form 4 hybrid orbitals, all with equal energy. So we'll form 3 equal bonds, and our lone pair will be in one of those atomic orbitals. So now let's place our electron configuration. To do this, we still follow the Aufbau principle and Hund's rule. We put 1 electron into each of our hybrid orbitals. All of these have the same spin, and we have 1, 2, 3, 4, 5 valence electrons for nitrogen. So now we go back and put our 5th one here, and we start to double up. We put those as opposite spins. So this would be what we would call the hybrid electron configuration for our central atom. Now, if you look at this, you see we're going to have a lone pair in one of our hybrid orbitals, and then we're going to have 3 unpaired electrons, which will allow us to form 3 covalent bonds. And that's what we need for ammonia. Here's our unpaired electrons, or excuse me, our lone pair of electrons in an sp3 hybrid orbital. And then we're going to have 3 sp3 hybrid orbitals, which can bond to our hydrogens. So as before, we're going to take our s, our 3p orbitals, and we form 4 sp3 hybrid orbitals. And those are going to be, if we have 4 electron groups, they're going to be tetrahedral geometry. So if you were asked to draw it, you'd want to draw it something like this. This is an sp3 hybrid orbital, and you can see our lone pair of electrons. This is an sp3 hybrid orbital, as is this and this. And each of our sp3 hybrid orbitals here is overlapping with a 1s orbital from our hydrogen. And you can see the pair of electrons is in the region of overlap between the atomic orbitals. So practice those, and also watch the next video, which will get into the different types of hybridization. sp3 hybridization is not the only type. We do have sp2 and sp hybridization. So be sure you are clear on the basics of valence bond theory.